Edition from weekly contest 199 from LEETCODE. So let's start. The first question is very simple. It states that you are given a string s and an integer array indices of the same length. So as you can see, you are given a string and some corresponding indices. Okay, so let's assume that 4 corresponding to C, 5 corresponding to O, 6 corresponding to D, and so on. And now you have to, what you have to do here is you have to sort, or you have to arrange all these indices according to its correct order, and then the correct word will form, or a new word will form according to this. From this word, when you will sort this indices, a new word will form and you have to output that new word. So that's the simple question. I'll take it on to the code part now. So what you can easily do here is you can make pair of all the characters and corresponding indices, then sort the indices and then print the new word. So that's what I've done. Take the vector of pair of integer and character, okay, and then what you'll do, you'll push at every position of the vector the indices which is stored in this vector and the ith character from the string, then sort the whole vector, and then the final answer is just, you can also, like, because you have to return it out, make a new string and iterate over the whole vector, and then because the character is stored in the second place, so ai dot second convert it to character and append it to answer and then return answer. So that's the first question, which is very simple. The second question can be do in two approaches. We'll like take the look on both the approaches. The question statement states that you are given n bulbs arranged from 0 till n minus 1. Okay, so if the ith bulb is on, it is corresponding to 1, and if the ith bulb is off, it corresponds to 0. Then what you can do the following operation, in which you can choose any indexes, and then all the bulbs starting from that indices till the last indices will flip this current state. So as you can see, then this is the target state you want to reach. So how many minimum number of operations of flip you have to do to reach the target string? I'll tell you more with this example. As you can see, because the initial string is all zeros, everything is off in the start. Okay, so everything is off, which is denoted by this configuration. Then what you can do, you can choose the third bulb. If you choose the third bulb from the last, then because all the bulbs starting from this will flip till the last, so it will become like this. Now what you'll do, if you choose the first bulb now, then it will make both of them on, but these will get off. And then what you can again do, you can again choose the second bulb. If you choose the second bulb, then this will get off and this will get on. So that is, if you see how we are doing, you can actually do this in the logic part also. So I'll tell you how. So let's assume that I'll take this example only. Okay, so what you can see here is, because everything initialized with 0 in the start, 1 2 3 4 5, okay, iterate over this state of the bulb. Because you have seen ones, find out the continuous stretch of ones. Okay, now because all of them are 1, you can just correspondingly do one operation and convert all of them to 1. Okay, because it is starting from last, you can also mark a j variable which tells us from where does this, we are finding actually subarrays of continuous subarrays of ones. Okay, now j denotes the ending point of this continuous subarray and I denotes the starting. Whenever you find a continuous subarray of 1 and j is the last point, then because you can flip all these characters in one operation, you can correspondingly flip all these characters and it will become like this. Okay, now because there is 0, you cannot do anything, just make your j point to this now, the next correspondingly starting position of 1. And because there is no more character, you have to flip this. Now to make this, if there are some more stretch like this, 1 1 1 0 1 1 1. So as you can see, if this is I and this is j, this is the next continuous stretch of ones. What you can do here is, if you, because you want to make this as a whole ones, so what you can do, you can first make this whole 1, because everything is 0, then this will become 1, and this will change its flip. This part will get flipped. So you can again do a flip on this part except this 3 part which you have to change, and then it will come to the target state we want to reach. Because as you can see, if this is changed, if we change this whole, because let's assume that it is 1 1 1 0 and 1, oh sorry, 0 0, because you have changed this. Now if you take this whole, it will become like 1 1 0 0 0, but we have actually make this one, but we don't want this. From this state has disturbed. So what you can do, if we will just flip this part, it will become like 1 0 1 1 1, and it will reach the final point, which are target. So that's the first tree. You can find continuous stretches of ones, and J denotes the last point, I denotes the first point, and whenever you find a continuous stretch, you can flip. If J is the last point, you can do it in one step, but if J is not the last point, you have to do in 2 steps. Okay, and that's the whole trick. You can, this is like somewhat a larger code. I have written down this code also. Okay, in which this is a total target. J is denoted by -1 because we do not know what's the last point of 1. It might happen that there is some 0 0 0, and then there is like 1 1 1. So what we will do, we will iterate from the last indexes to the first index, and if what we find that the target value or the target value is 1 and J is -1. J, the last index is -1, because it means that we haven't find the last index or the starting of the continuous subarray. Then we make our J equal to I. This is the last index of the continuous subarray. Else, if we find that the target is 0, because when we know, how we know that this is the continuous stretch one, we will only know that when we reach a 0 point, because we see that 1 1 1 and then a 0, which means that this continuous subarray has finished. Continuous subarray of like ones has finished, and then we have found a 0. So this is the ending point or the starting point, this is the ending point. Okay, so if the target value is 0 and J is not equal to -1, in which means that we haven't find our last index, then this is the J. Then what we can do here is, J is not equal to -1, which means that we have found out our last index and we have found out our starting index only. So we will check that if J is last index, or the last index is, then the total will increase by 1 only, as total will increase by -2, and we will again make our J equal to -1. Okay, and we'll do the same for if we just find out J target value equal to 0 and we haven't found this one. Okay, but let's assume that there are all ones, and we'll come out of, we will check that, okay, we will make our J point to the last value, and then our I will go out of this iteration, and we haven't found a starting value. So what we'll do, we will also check that in the end, if we go out of the value and we haven't done anything, we'll also check that whether there is some I left, which is this. So you can do it in one flip only. Okay, so this is somewhat a little bit logical, but the code is lengthy, in which if J is equal to -1, then if it is the last index, total plus plus, which we have done the same, else total plus equal to 2, and the answer is 2. That's the whole trick. You are just finding out the continuous subarrays of size 1, or continuous subarrays which are only having ones. Okay, the next logic can also be, because if we just found out that the state is 0 1 0 1. Now if the consecutive elements are not same, if the two elements which are not same, then we have to do a flip to reach this state. Why? Because let's assume that there are 0 0 0. Okay, now if we want to make, because these two elements are not same, we have to at least do one step to make this reach this state. So we can do one step. Then because there is again not same, then we have to do again one step to reach this state. Okay, so what this means here is, for every change, for every bit which is changed, and also we have to append a 0 in the start. For this logic we have to append a 0 in the start, because we are missing actually one more flip. Okay, because let's assume that there are all ones and then a 0. We will check every consecutive element. This is same, this is same, this is same, and if there is no 0, will come out of this for loop, and there is no change. But because everything is 1, we have to do at least one flip. We have to do one flip to make it all zeros. Because there is all zeros, we will do one flip to make it all ones. And thus what we can do for doing this, we can append a 0 in the start of the string, and whenever we will check the consecutive element, if there is a change, if the consecutive elements are not same, we will append our answer, or we will increment our answer. So that's the second logic I written down here. It's a very shorter logic in which also write it clear. We will append in the target, in this target string, we will in the append in the start a 0 again, and then what we'll do, total is the total number of steps. We will start from back to the front. If the ith element and the previous element, I minus 1 element, are not same, then increment the total and just return the total. That's also a simple code. Okay, you can also come up with both the ideas. Okay, now move on to the third code. The third part, the third question states that given the root of a binary tree, okay, and an integer distance. Now what you can do here is a pair of two different leaves of binary tree is said to be good if the length of the shortest part between any of them is less than or equal to distance. So what does this means actually here is, so let's assume that the distance between any two leaves, you have to find out the distance between the leaves, two different leaves. So what is the distance between 3 and 4? 1, 2, 3. So what this means actually here is, you are given a binary tree and you are given a distance. You have to find out how many leaves, distant leaves, are having a distance 3 or less than 3. I hope you understand. So as you can see in this tree, this is a binary tree in which we have to find out the different leaves which has a distance of 3 or less than 3, because these are the 4 leaves. This can be a distance, this can be a distance, this can be a distance, and so on. And thus, as you can see, if these are the distances, because this is 1, 2, 3, 4, distance between 4 and 6 is 4, but we can only find out distance between which is less than or equal to 3, and thus there are only two pair, which is 4, 5 and 6, 7, which are having distance equal to 2, and thus the answer is 2. So we have to find out these. So let's move on to the drawing board to make it more clear. This question comes to me when I see that the constraints are very small, the constraints are small enough, and also what you can observe here is, you are just looking for the children, because, okay, let's assume that these are the two leaves. Now if you want to find a distance between these two leaves, we have to find out its parent, because as you can see, okay, distance between this and this is this. So it will always find, if we know the parent of this, of any the leaves we want to find out, then it is just the distance between this parent, the height of this from this parent, and this from this parent. This is the addition, and this is the whole trick. So if you know for every parent what are the distance of its left child and what are the distance of its right child, what I mean by it is, for every node, if we know what are the leaves it has on the left side and how many leaves are having it on the right side, and what are the distances of those leaves, we can easily find out. Because let's say that for this node, we know that for the right or for the left side it has two leaves which has the distances 2 and again 2, but on the right side it has one leaf which has distance equal to 1. So what you can easily do here is, you can just iterate over for every node. You can find out, because we have these leaves, what are the possible number of good pairs we can form. We can form a good, if the distance is 3, we can take a pair of 2 and 1 and 2 and 1, and the total number of good pairs are 2. Okay, so iterate over, just find out the left leaf distances, right leaf distances of every node, and then what you can do, you can check that for every pair, because for every node we can add these distance with this distance, and if this distance is like less than or equal to d, you can form a good pair. So what you can do, you can recursively iterate over the whole tree. For the children or for the leaves, what you can see, because it is the because for the children there is no way you can, because there is no left or right tree, this is the leaves. So what you can do for the children, you can just push the distance which is 1. Okay, because this is the distance. Now for 2, now when we come to 2, the distance, we'll check that whether it has left child, whether it has right child. Yes. What you will do, you will take the distance of its left child and right child, iterate over them. We will make a pair that add every child, every values in this vector to the other vector. So 1 plus 1 equal to 2, which is less than 3. So this will form a good pair. Okay, you add this. Are there more pair we can form? No, we cannot form more pair. So what we will do, we will take these values and send them to its parent, because these distance will send to the parent, because this parent will send or help the upper parent of this node to find out the distances of its leaf node. Because for this node, how we can find out how many leaf node it has and what is the distance? So what we will do, for every node, what we will do, we will send a vector, and the vector will store all the leaf values. Because the leaf value is this, we will iterate over all the leaf values and add 1 to it. Because we are moving one level ahead, the distance will increase by 1, because for this node now the leaf distance is equal to 2 and we have stored the leaf distance equal to 1. So what we will do, when we move one level ahead in the recursion, what we will do, we will take all the leaf nodes which are stored or which we have for the left child and the right child, add 1 to it. Now it will become 2 and 2, and you will send this vector to this node. Now this node will store that I have seen 2 leaves of length 2, and this will send that I have seen 1 leaf of length 1. Okay, so as you can see, 2, 2 and 1. And thus for this node now, it will check how many leaf nodes are there on its left child, which is 2 and 2, how many distance leaf are there on the right child, which is 1, make pairs, this and this can form pair, this and this can form pair, and this, and what you can do here is find a total number of pairs which will be less than or equal to distance and add it to the total 2 and 3. That's the whole logic. I'll take you on to the code part now. The code is, you can make answer to be a global variable, and then this is the this is the count pair function. We will make the distance also global, which is the distance between the two nodes, and then run a DFS on the root node, and then return the answer. And DFS function will return a vector. We will send the root as the starting value. We will make a new vector of array, vector of integers, which will store the distances of which will store the heights of every leaf node from the particular root node we are given. If the root is null, then we will just return the empty vector. Okay, else what we'll do, we'll recursively call this same DFS function on the left child or on the right child. Then what we'll check that if the left child and the right child both are sending a vector which is empty. Because as you can see, if we call for the leaf node, the DFS on the leaf node, because there is no node here and no node here, this is null, and for the null we have seen that we will return the empty vector, and we will return an empty vector here, empty vector here, and because there are empty vectors on both of the sides, it denotes that this is a leaf. And what we'll do, if this is a leaf, we will push back, as we have told you, because it is a leaf, we will push back the distance of this leaf node with respect to itself, which is 1, and then we will return this new vector, because for the leaf node there is no left and right child, we cannot find out more pairs with respect to this node, so we will just add the distance of this leaf node, which is 1, and return this vector. Then what we will do, else for if this is not a leaf node, it is some random node in this whole tree, then what we will do, we will find out its left, all the total vectors or distances or height for the left child and for the right child, make a O of n square loop, and for every left and right value we will check that whether the value is less than or equal to d, increment our answer. And after incrementing the answers, what we'll do, we will add all the pair or all the leaves which are on the left child. Okay, iterate of all the leaf distances on the left child, add 1 to its value and add it to the A vector, which we will send via its parent, and do the same for its right value also. We are just iterating over the left and the right child leaves and adding one value to it because we are moving one level ahead, and then return this A. I hope you understand the logic and the code for all of the three questions. If you still have any doubts, please mention down. Thank you for watching this video. I'll see you in the next one. Keep coding. Bye.